Welcome everyone. In this video lecture, I will discuss finite Fourier cosine transform. In my last lecture, I will discuss about finite Fourier sine transform. So today we will define finite Fourier cosine transform. So here we are given a function fx, which is defined in the finite interval 0 to L, and it also satisfies Dirichlet conditions in that interval. In that case, finite Fourier cosine transform of the function fx is denoted by fc of fx, and it is defined as integral 0 to infinity fx cos p pi x upon L dx. We also denote this by fcp, or this can be written as fc bar p, where p is integer or it may be 0. If L is equal to pi, in that case, sorry, I have do a mistake here. Actually, it should be L, not infinity. Yes. If L is equal to pi, in that case, Fourier cosine transform is 0 to pi fx cos px dx. Okay. We can also define the inversion formula for finite Fourier cosine transform. If we are given this function fcp, if we are given fcp in the interval 0 to L, then we can define its inverse Fourier cosine transform, inverse Fourier finite cosine transform, which is equal to fc inverse of fcp, which is equal to fx, and it is defined as 1 upon L fc0, means you can also write this as fc at 0 plus 2 upon L summation p is equal to 1 to infinity f c bar p. It is same as fcp cos p pi x over L. Okay, so where this value, this is nothing but fc0 is equal to where fc0, or you can also call it as f c bar 0 is equal to 0 to L fx dx, because p is equal to 0, so cos 0 is 1. That's why we have this expression. So you can remember some formulas while doing the problems related to finite Fourier cosine transform or finite Fourier sine transform. That formulas are very useful while doing the numerical problems. That useful formulas are we have I have told you yesterday that sine n pi is always 0 and cos of n pi is always equal to minus 1 raised to the power n, where n is an integer. Third is sine of 2n plus 1 pi by 2 is equal to minus 1 raised to the power n, and cos of 2n plus 1 pi by 2 is always 0. Similarly, we have e raised to the power ax sine of bx dx. Its integration is e raised to the power ax over a square plus b square, a sine bx minus b cos bx. And similarly, we have cos of bx in this integration. Then we have e raised to the power ax cos bx dx. It is equal to e raised to the power ax over a square plus b square, a cos bx plus b sine bx. And if I have this type of integration, e raised to the power minus ax sine of bx, in that case, and if I have the limit 0 to infinity, so in this case it will comes out to be b upon a square plus b square, because if you put minus a here, okay, uh, this a will be replaced by minus a everywhere, okay. Then we apply the limit, then upper limit, at upper limit the this whole expression will be 0 because e raised to minus infinity is always 0, and at lower limit this term is 0 and this will be only b. We are left with b, and e raised to power 0 is 1, so we have b upon a square plus b square. This is a formula that you can memorize. And similarly, if we apply the limit in cos formula, then we have a upon a square plus b square. तो आप इन फॉर्मूलेस को याद रख सकते हैं. आप ये फॉर्मूला भी याद रखिएगा. साइन हाइपरबोलिक x इज इक्वल टू e raised power x minus e raised power minus x whole divided by 2, and cos of hyperbolic x is always is equal to e raised power x plus e raised power minus x whole divided by 2. So keeping in mind these shortcut formulas, let's do one example. Yesterday I have discussed finite Fourier sine transform of the function 2x. Let's find the finite Fourier cosine transform of that function. Finite Fourier cosine transform of fx is equal to 2x, where x lies between 0 and 4. So by definition of Fourier cosine transform of any function fx, is defined as integral 0 to L. So we have 4 in place of L. Fx is 2x cos p pi x over L. So we have p pi x over L is 4 dx. Okay, so we integrate this by parts. Fourier cosine transform of the function 2x. 2x sine p pi x over 4 whole upon p pi over 4 minus 2, 2x का derivative 2, then integration of this is minus cos p pi x upon 4 whole p square pi square upon 4 square, and we apply the limit from 0 to 4. So we have 8x upon p pi sine p pi x upon 4, 32 upon p square pi square cos p pi x upon 4. It is equal to 32 upon p pi at upper limit. This is we replace x by 4, so it will be sine p pi plus 32 upon p square pi square cos p pi. At lower limit this will be 0 and this will be 32 upon p square pi square. So I have told you that sine n pi is always 0. So this is 0, and cos p pi is minus 1 raised to the power p. So we replace this by 32 upon p square pi square minus 1 raised to the power p, 32 upon p square pi square. So we can take 32 upon p square pi square common, minus 1 raised to the power p minus 1. This will be the answer. Now next example is find finite Fourier cosine transform of fx is equal to x square, where x lying between 0 and pi. So Fourier cosine transform of the function x square is 0 to pi x square cos p x dx, because pi cos p pi x upon pi, so pi will cancel the pi in the denominator, so we have px here. So we integrate this by parts. X square sine px over p minus 2x cos px over p square plus 2 minus sine px over p cube. This is a shortcut formula फर्स्ट फंक्शन, इंटीग्रेशन ऑफ सेकंड फंक्शन, देन ऑल्टरनेटिव साइन हमें यूज करने हैं, प्लस माइनस, और इस फर्स्ट फंक्शन का हमें डिफरेंशिएशन करना है और सेकंड का इंटीग्रेशन करना है। फिर आप इसका डिफरेंशिएशन करेंगे और इसका इंटीग्रेशन करेंगे। या जब तक आपको करना है जब तक डिफरेंशिएशन 0 ना हो जाए। This is pi square sine p pi over p minus 2 pi, it will be plus cos p pi over p square minus 2 sine p pi over p cube. At lower limit all will be 0. So we have sine p pi 0. We have only 2 pi minus 1 raised to the power p over p square minus this will also 0. This will be 0. We have left with this, where p is 1, 2, 3 and so on. So these are the examples based on finite Fourier cosine transforms. I hope you understand the lecture based on this finite transform and the examples that I have done. If you like my lecture, please press the like button and share it, and you can also subscribe my channel to get the notification of any new video on this channel. Thank you once again.